I wish I had a bigger board. Okay, so the standard error of the mean, Sx bar, is 15 divided by the square root of 20. Okay, so what is that number? 15 divided by square root of 20 is 3.35. 3.35. Okay, so so what's the z-score for a sample of 20 people? So for the z-score, I'm going to substitute the standard error of the mean. So the x bar minus mu divided by Sx bar, this is for a sample. The z-score would be 112 minus 100 divided by this standard deviation. Not the 15, but the standard deviation for a sample of 20 people. The standard error of the mean. Divided by 3.35. Alright, so this is going to be 12 divided by this number. And 12 divided by the other number is 3.58. So this is about 3.58. Alright, so the odds or the probability of getting 20 people at random with an average IQ of 112 is actually a much higher z-score. And what's the tail probability for 3.58? I think by coincidence I actually managed to find something very near the top of what the book has. So in the book, if you look for a z-score of 3.58, we go down to 3.5 and go across to the 0.08 column, and we get 0.002. So the tail probability is 0.0002 or 0.02%. All right, so that's one chance out of 5,000. So here's the point. Suppose we made this assumption that Math 160 students were not smarter than the average human out there, the average person on the street. All right, and then we go measure their IQs. And we find that their average IQ is 112, not 100. And we say, well, maybe that was just unusual. Maybe that was very unusual. I somehow managed to get 20 people with an average IQ of 112. Well, how unusual is that? It's one chance literally out of 5,000. 0.02%. And so, okay, well that's only going to happen one time out of every 5,000 classes. If there is no difference between Math 160 students and the average population. Okay? You think, well, that's ridiculous. That's astronomically small. So we will now reject the idea that Math 160 students have an average IQ of 100. We reject that assumption because that assumption is probability of that assumption being true is actually astronomically small. So we're going to conclude that Math 160 students really are smarter than the average population. Alright, so you just got a foreshadowing of hypothesis testing from Chapter 7. If you didn't quite follow that so well, bear with me, it's okay, you don't need it yet. We will do a bunch more of these when we do Chapter 7. Alright, I'm going to take a short break and we'll wrap up try to wrap up this video. Well, to summarize the standard error of the mean, it's not really the standard deviation from the means of many samples. It's an estimate of the standard deviation of a sample mean, of a sample mean. And you can calculate it from a single calculation, as you've seen here. Alright, so what have we done in this chapter so far? We've introduced measures of central tendency, primarily the mean. The mean is the average, and it describes the center of the data, and it's the most useful calculation because we can use that to in lots of statistical formulas and theorems. The standard deviation we also calculate as a measure of dispersion. How wide is the data dispersed? And hopefully you're starting to get a sense of what that means. We need to describe how far spread out the data is. And it turns out that one number tells us an awful lot. Except the standard deviation is not so interesting as the standard error of the mean, because we are interested in samples, not individuals, but sample measurements. So, okay, I'm going to take a quick look in the book, and other than looking at some examples, I just want to make sure I've covered all my bases. So I think I have. All right, I'm going to stop this video, and we'll do a separate video for examples out of Chapter 4. So, I'll see you in the example section.